This is a lesson video then for exercise 14E.1. There's actually two parts, as the name implies. We're looking at problems with the fixed point iteration method initially. And there are, as I said, there's a second video coming as well, so have a look out for that, probably tomorrow. So you will recall that we've previously seen that we can draw what this I call a cobweb diagram, and we did this actually at Cowley from memory. A cobweb diagram, and this was the staircase diagram. And sometimes the staircase diagrams or the cobweb diagrams work. This first one, for instance, you can see my first route here, and you remember I said from you go up to the curve, and this red line, even though it looks straight, this is actually my curve, and I'll talk more about that in a bit. And this is my line y equals x. This is what I called line. So I go up to my curve, across to my line, down to my curve, across to my line, and you just keep going curve to line, and so you can see it's definitely getting closer and closer to the root, and it will eventually get the root. And this represents the root that we want from another equation. So this one right here we would describe as converging, which basically means finding the root. So it converges. This one, on the other hand, I'm going to say diverges. Basically doesn't find the root, and I'll show you via the picture as well. It doesn't matter if this one's a staircase. The staircase can converge to the root. Sometimes they diverge. Likewise, a cobweb diagram. Sometimes it converges, sometimes it diverges. But you'll notice my first guess here is x0, and on the face of it, that root is really close to it. You should find it. But what you'll notice is actually, if I go up to the curve, to the line, up to the curve, I'm getting further and further away, and that's not coming back. That one's not going to find me the root, which is called alpha in this case. So that's what we're trying to do. We're trying to understand when and why we might find that it works and when it doesn't. Okay, so this would generally be described as the limitations. So sometimes it fails, sometimes it works. Sometimes it finds a root, but it's not the root we want. It's the wrong root. I think we saw that in the last exercise on Newton-Raphson. So graphically, I've got this situation here. I start with my first guess, and you can see bit by bit it's going further and further out, and that's going to carry on spiraling out. This cobweb diagram fails. This one's a diverging one. And here again, on this one, I chuck the number in. That's like the one we just had, it just misses. And this one, curve to line, it misses again. Now you're kind of getting the idea that I'm not sure what I could throw in at that. Would it ever give me the root? And there is a rule which basically says it's all to do with the steepness. The steepness of the curve. And in this case, it's the blue line. And that blue curve, the gradient or steepness of that blue curve is effectively what determines whether or not this converges or diverges. And it's a bit tricky because you don't know where the root is, but you get an idea that you might know it's roughly this number, and whatever your first guess is, we might be able to use that and work out how steep the curve is at that point, and say whether or not we expect it to work or whether we expect it not to work. So that's what that last bit basically says. And the rule essentially is that the gradient has to be between 1 and -1 at the root. So I've described this here, and I've said this g is the gradient of the function, which is the curve, that blue line as we just saw. So this is the gradient of the curve at the root. So at alpha has to be between 1 and -1. And basically that means it's quite a shallow graph. Now if you think about it, it's all to do with the fact that on these we always use the line y equals x. And of course this has a gradient of 1. So if it's more than 1 it fails. If it's less than -1 it fails. And it's because of this steepness aspect of the line y equals x having gradient 1, which essentially does it. So there it is in black and white, if you like. It converges if the gradient is less than 1. Notice here I'm saying the modulus of the gradient, so ignoring the negative part. If the number you get is less than 1 and it's sufficiently close to the root, then it will converge. And here it says the opposite, it will diverge if the gradient is more than 1. And then remember, this is positive or negative magnitude. So let's have a look at an example and see what we can come up with here. I've got 3 examples for you. So the first one says I've got an equation x cubed plus x squared equals 25, and it says show there's a root. Now this is the change of sign method. So for part A, I'm just going to try to change a sign. And if you remember, if you try to do change of sign, you effectively write a function and you get it all onto one side. So I'm going to write x cubed plus x squared minus 25 is my function. And I'm going to put 2 into that initially. Gives me 8 plus 4 minus 25 equals minus 13. So I've got a negative number. If I put 3 into that, I get 27 plus 9, well that's 36, minus the 25 is 11. So there definitely is a change of sign here, and therefore the root definitely belongs to the interval 2, 3. Now this next bit, we've not done this. This iterative formula basically is a rearrangement. Let me just go back to this. So we had initially x cubed plus x squared equals 25, and the trick is to look at what they've got. Well, they've got a cube root on there, so the obvious thing then is to go, well, x cubed equals to 25 minus the x squared. Now check it up here. Therefore x is equal to the cube root of 25 minus x squared. And notice what you end up then doing. You make it an iterative formula by saying the ones on the left, xn plus 1, equals the ones on the right will have an xn, so it's 25 minus xn squared. So it's really just a rearrangement with a couple of letters thrown in at the end. So that's the iterative formula, and it says use it when you've got x0 equal to 2.5. So I'm just going to rewrite that on the other sheet. Oh, there's the graphs, by the way. I'll come back to that in a bit. So xn plus 1 equals, let's have a look, it's a cube root of 25 minus xn squared. And it tells me to start with x1 equals, or x0 it calls it 2.5. It doesn't really matter what you call it. The first one is 2.5. And we've seen how to do this. You type it in as 25, or you type 2.5 equals, and 25 minus the answer squared. So let's just do that. 2.5 equals, so now I want the cube root of 25 minus the answer squared equals, and I get 2.65. What does it want me to do? How many? It just says to find the solution. So I'm going to write the first one. And again, in the exam, sometimes they say they want you to give all the answers. Sometimes they just want the final answer. 265, I think it said 4dp, 66. Yep. And then, so I'm going to press equals, equals, equals. And eventually, I get the root to be, notice I've written alpha, 2.6260 to 40p. Oh, I got 6258 on that. I wonder if I just keep pressing equals. I'm not there yet. Oh yeah, I wasn't there. There you go. I thought I'd pressed it enough time. And yeah, so if I press it more, that is a bit of a warning, isn't it? 6258. If I kept on pressing it, I would have got more. So then it agrees, and then I've got my answer. So that was, so notice this then. This is the line y equals x. And this curve here, this now in red curve, I keep on switching the colours, this is what I'm calling g of x. And it's the gradient of this line that is important. That's why this one has got me a root. G of x was equal to this cube root stuff. Yeah, I'm not going to write it all out, but this cube root thing here, that's my g of x. And notice near the root, it is very shallow. It happens to be going down, so it's shallow and negative, but essentially that doesn't matter. That's what we're looking for. Here's another example. It says example 2 at the top on this. So it says show that there is a solution between there and there. Okay, so let's get it all on the same side. We'll call it f of x. And then I'll do f of 1. So that is log of 1. I can do it out of that calculator. Minus 2 1s plus 3. So this is plus 1. And f of 2 is obviously log of 2. Let's just type this one straight in my calculator. Log 2, close bracket, minus 2 2's are 4, plus 3. It is negative, it's minus 0.307. So therefore we've got to change the sign, and therefore we have a root which belongs to the interval 1, 2. Let's do the iterative formula again. Now, let's have a look what we've got initially. Right, I've still got the logs. I'm not getting rid of the log. Oh, I see what they've done. All they've done is they've said log x equals 2x minus 3. And they, rather than thinking normally where you'd move the 2 over, they've said, oh, that's x plus x minus 3. So I'm going to move one of them over, and I'm going to move the 3 over. So it's a bit unusual. You don't normally do this. So log x minus the x plus the 3 equals x. So that one is still here, but the other 2 bits have moved. And therefore I can finish off by writing xn plus 1 equals, well, it's the log of xn minus the xn plus 3. We're not used to doing that. So we're going to say x0 equals 1.5. I'm going to do the same thing again. It wants the solution. So I've got 1.5 equals, and it is the log of the answer, close bracket, minus the answer plus 3. And I got 1.905 this time, and I'm just going to press it. I'm not going to make the same mistake as last time. I'm going to make sure I press it enough times. And then they say, sometimes the advantage of Newton-Raphson, you get an answer very quickly. And sometimes on these you don't. And so I'm having to press this like 20 times at least. But eventually I think I've got my answer. Alpha is 1.7915. That's what I reckon anyway. 7915, yeah. The last one then. Now, I might need to go on. I've got about 3 minutes left on this, so if I have to do a second video, I will. Notice this has already been rearranged. X cubed, it says here are 2 possible rearrangements. So I don't have to do that part, and whether you can do that might be something you could do. But in order to do this, I'm going to think of this one as x equals minus 5 lots of x squared plus 2 to the power of minus 1. And this one, of course, is minus 2x plus 5 to the power a third. Now what I need to do, now this is effectively giving me a g of x for the first one, and this is another g of x for the second one. So I remember said you have to find g dash of x. So that actually means we can use the chain rule here. So the minus 1 comes to the front as a power. It's going to be 5 lots of the x squared plus 2. I've got to knock off a power, so that's now to the minus 2, and now I times by the differential of the bracket, which is 2x. So this gives me 10x over x squared plus 2 squared. And this one, I'm going to find g dash of x of this, and it's a similar trick. It gives me minus a third of 2x plus 5 to the power of minus 2/3. Don't forget I've got to times by 2. So that gives me minus 2/3. In fact, I'm just going to write it like that, minus 2/3 of 2x plus 5. It's not very nice no matter what I do to the minus 2/3. Now, if I'm going to do this then, if I want to know whether they will produce a root, it says near the point minus 1.3. So I'm going to find g dash of minus 1.3 for both these expressions. G dash of minus 1.3. I'm going to type them in. I'm going to do that by pausing first. So I've just typed them in. So I'm going to write down what I've got when I've done it. So when I've typed minus 1.3 into this, I got minus 0.955. That's a minus at the front. And this one I got minus 0.372. When you put 1.3 in, minus 1.3. Critically, both of these values are between a minus 1 and 1. So they both should have a root. So what's it say? Both converge to the root. Yeah, because of that. So your job is to start looking at exercise 14 here. You won't be able to necessarily finish it there yet, so do what you can. I'll do another lesson probably tomorrow, and you'll be able to do the whole exercise then. So best of luck.